So let's talk about covariance and independence. Two things to say. Okay, first of all, if X and Y are independent, we know that. That implies that their covariance is 0. Okay, so great. If we know that they're independent, we know their covariance is 0, and if we have a bunch of covariances in a big old expression, we don't have to worry about them because they all equal 0. That's great. Thing 2, though, less important, more just like a fact, is that the covariance of X and Y being 0 does not necessarily imply that they're independent. Okay, so sort of do both of these things. What I'll do is I'll demonstrate this in the context of a simple random variables, pair of random variables, each of which takes 2 values, kind of our standard workhorse example that, as is generally the case, will give us the logic of the overall result. And then I'll show you an example that lets us know why the covariance of 0 doesn't necessarily mean independence. Okay, so let me start with as much space as possible for my little example here. So what I want is X taking values X1 and X2, and Y taking values Y1 and Y2. And I want to build into this example X and Y are independent. And what does that mean? It means that the probability that X is X1 and Y is Y1 is just the product of those individual probabilities. Okay, so we're assuming independence means right now I can just say this is probability that X equals X1 times the probability that Y equals Y1. Here we have the probability X equals X1. It's the probability Y equals Y2, probability that X is X2 and Y is Y1, and the probability that X is X2, probability that Y is Y2 here. Okay, so this is reflected in the PMF, okay, where the probability of xy equals the probability of x times the probability of y. Great. Okay, so fine. We have our PMF. Let's use that formula to calculate covariance. Okay, so the covariance of x and y, we are told, is the expectation of the product minus the product of the expectations. Good. So I can find the expectation of the product here from the joint PMF. And then I can subtract off the means. So just going about that, working on the expectation of product of x and y. Okay, well, it can be x1, y1 when that happens with this probability, plus x1, y2 times the probability that x is x1, the probability that y is y2, plus x2, y1 times those probabilities, x2, y1. I'm going to go to the next line here, plus the last possibility here is that, put my outcomes first before I write the probabilities. We have x2, y2, probability x is x2 times the probability that y is y2. Okay, all of this is the expected value of the product, right? The product can take this value, that value, that value, or that value with this probability, this probability, this probability, or that probability. And the joint probabilities are the product of the marginals because they are independent. Great. So that's my first term in the covariance. And then I'm just subtracting off x bar minus y bar, whatever they are. Okay. I'm going to do some factoring here. Let me factor out, in this first expression, I want to factor out the x1s and the px x1s here. Okay, so from these two terms, I want to factor that out. So that equals x1 px x1. And so what am I left with when I factor that out? I'm left with y1 times py y1 plus y2 py y2, that's a plus y2. Okay, I've got two more terms here, and I want to factor out the x2, probability x2 from these two terms. Plus x2 px2. And when I factor that out, oh, look, I've got y1 p1 y1 here. Plus y2 py y2. And still subtracting off the x bar, y bar. And close my parenthesis here. Okay, this is one of those fun little algebra exercises where things get really messy and then they collapse in a very satisfying and neat way. And to see that, just notice what I've got here. What I've got there is the same thing. Okay, so again, I can use the distributive law here. Back to this, that distributive law of real numbers comes in so handy so often. I've got this common factor in the two terms, so I've got really this plus this times their common factor. x1 px x1 plus x2 px x2 times the common factor is y1 py y1 plus y2 py y2 minus x bar y bar. Okay, now let's just see what we've got here. x1 times its probability plus x2 times that probability, that is expected value of x, that is x bar, multiplied by y1 times the probability of y1 plus y2 times the probability of y2, that's the expected value of y, multiplied by x bar minus y bar equals 0. Okay, so that's hard to argue with there. If we know that x and y are independent, and in reality, what we're really talking about is if we're willing to assume that x and y are independent, then we know that the covariance is 0. Lovely. But not the other way. And again, I want to sort of give some nuance here. The fact that if we know x and y are independent, we can be sure the covariance is 0. That is hugely helpful for understanding regression analysis and regression statistics. Very big deal. The fact that the implication doesn't work the other way is not going to loom that large in your life, but it is true, and you should know that it's true. And so we'll see an example here that lets us see. But you can have a covariance equal to 0 and not have independence. Okay, So the example here I'm going to give you is x takes values -1, 0, and 1, and y takes those same values, x, y, and the probabilities look like this. A little checkerboard pattern here. Oh, while we're at it, why don't we put the marginals? Okay, so probability that x is -1 is 0.25. The probability that x is 0 is 0.5. The probability that x is 1 is 0.25. Same deal for y. It's symmetric between the two variables here. 0.25, 0.5, 0, 0.25. Okay. I'm not going to write out all the calculations here. I think they're pretty easy to see. If you're not following every step, just write it out yourself with pencil and paper. But I'm going to assert here the expected value of x is 0. Okay. It's 0.25 times -1 plus 0.5 times 0 plus 0.25 times +1. So the -0.25 and the +0.25 are canceling each other out. And the same thing is true for y. Okay. And I'm also going to just assert here that the expected value of their product is also 0 because there's no combination of x and y's that has positive probability that isn't equal to 0. Okay, so one way that the product could be not 0 would be if they're both -1, that's 0 probability, or 1 and -1, that's 0 probability. The other one's 0 probability, the other one's 0 probability. Or saying the same thing, maybe a more direct way, is everything that has some probability, positive probability assigned to it, has at least one factor of 0. So there's a 0 here. Positive probability here, but x equals 0. Positive probability here, but y equals 0. Positive probability here, but x equals 0. Okay, so all of this is enough to let us know that the covariance equals 0. Okay. So we would have the expected value of the product is 0 minus the product of the expected value is also 0. 0 minus 0 is 0. We got 0 covariance here. Okay, but in this particular case, x and y are not independent. Okay, and to see that, I'm going to assert and then show that the probability that x equals 1 is not the same as the probability that x conditional on y equals 0. Okay. Just reminding ourselves, this is what it means to be independent. If they were independent, knowing that y equals 0 would not change our probability associated with x. And I'm saying that in this case, it does, because the probability that x equals 1, the marginal here, where is it, is 0.25. Probability that 1 conditional on y equals 0 is the joint probability, right? X equals 1, y equals 0, divided by the probability of the conditioning event, probability y equals 0 here, and the probability that x equals 0 and x equals 1 and y equals 0, that's this probability here is 0.25, and the probability that y equals 0 is 0.5, and that is 0.5. These are not y are not independent. So that's kind of wrapping up the remarks I want to make right now about covariance. We've got a couple more points to cover in the lessons for today. So I'll see you in the next video.